Okay, so I had a request from one of the esteemed students in this class to do problem 28 and 29 from the book because problem 30 uses 28 and 29. So let's see if I can find what I wrote on these two problems. Ah, here it is. Okay, so maybe you've read this, perhaps you haven't. This is a technique in getting people to answer questions truthfully when they might be embarrassed about answering the question. Maybe the question is, have you used performance-enhancing drugs? I don't know. Maybe nobody in this class has, but there may be some embarrassment on the part of the person being interviewed in answering truthfully. So you give them a question randomly. Question one is, is it true you have characteristic A? Well, you did A. Question two. Is it true you didn't do A? Or maybe is it true you have property A, or is it true you don't have property A? Something like that. So the person being interviewed is given one of these two questions randomly and answers either question one or question two, but the interviewer who is recording the answer doesn't know which question the person is answering, and the person being interviewed realizes that the interviewer doesn't know this, so there's no, he doesn't feel any embarrassment about answering truthfully. Okay, so, but this leaves the interviewer with a problem of deciding what the data mean. How do you find out, for example, how many people did A or how many people have characteristic A from the outcome of the interviews? So something like a coin is tossed. So the P is the probability that question one is asked. And of course, 1 minus P would then be the probability that question 2 is asked. We do this multiple times, n times, and then capital R would be the proportion of positive answers. Where a trial would be an interview. So we know this outcome. We know capital R from the interviews. And what we want to decide proportion of the population who did A or have characteristic A, if it's something like that. Okay, that's what we want to decide. So we want to use R somehow to make some inference about Q. So if we know, so this is part A, if we know P and Q, what is the probability that the respondent answers yes? Or well, what's the probability of a yes? I'll use Y to indicate the event that the interviewee answers yes. What's the probability of yes given question 1 is the one the interviewee is answering? So the question is, did you do A, or do you have property A? What proportion of the population has property A? Q. So the probability of answering yes when asked question 1 would be Q, little q. Because that's if you pick a person at random, let's assume they answer truthfully. This filtering method should get people to answer truthfully. It's just if you pick somebody at random, what's the probability that they have property A, or they did A? It would be Q, little q. Question on that? And what would be the probability of yes if they're answering question 2? Yeah, 1 minus q. Because that's a proportion that would not have property A. Right? What's the probability that question 1 is the one that's asked? P. And the probability that question 2 is the one that's asked? 1 minus P, right? So the probability of a yes answer would be the probability of a yes answer given question 1 is asked times the probability that question 1 is asked. Sorry. Plus the probability of a yes answer given question 2 is asked times the probability question 2 is asked. So this would be Q times P plus 1 minus Q times 1 minus P. And if you multiply that second part out there, you get that, and then we should collect. Let's collect the terms that have Q. I see a stunned look. It's okay? All right. If I collect the terms that have Q, that would be this, this, and this. And that would give a Q times what? Well, P 2 times, so 2P. And then minus 1. Plus, and what's left? 1 minus P. And that's the probability of a yes response. And we'll call that little r. Okay. So we can solve for Q to get this. I solve for Q because that's the thing we're interested in. And now we want to find an estimate for little q. So the data we collected can be summarized by capital R. I think that's all we're interested in, the proportion of the respondents who answered yes. Well, capital R is an estimator for little r. What would this be? Well, what is capital R? How could we describe this? Suppose we interviewed n people. And we record the information this way. Xi is 1 if the ith interviewee said yes, and it's 0 if he said no or she said no. And then R would be what? One over the number of interviews or interviewees times this, right? This would be a count of how many yeses we got. And 1 over the number of interviewees times the number of yeses would be the proportion of yes answers. What's the probability that Xi is 1? It's the probability of getting a yes. It's little r. And of course, that's 1 minus the probability Xi is 0. So what's the expected value of capital R? How do you take expected value of something like this? Well, you get 1 over n times the expected value of the sum. That'd be 1 over n times the sum of the expected values. And what's the expected value of each term? It's r, right? With a random variable like this, the expected value is r. So you get r, how many times? N times. So this would be, when you take expected values, you get nr divided by n is r. And what about the variance? Actually, so just to, what's the distribution of this random variable? Binomial with parameter n and r, right? So the expected value of that would be nr. What's the variance of this? N r times 1 minus r. What would the variance of this be? Nope, not quite, because you have to square this. It'd be r, 1 minus r over n. Again, because this is binomial with parameter n and r, the variance of this would be n r 1 minus r. When we multiply by this, we have to square it when it comes to taking variances. We get 1 over n squared times n times r times 1 minus r. That's this. Okay, so I think that was part B of this question. Or Or was it C? C? Part C. What was part B? Oh, find Q. Oh, okay. All right, so that's part B. Here's part C. And then part D is find an estimator for Q. Is that right? Is that part D? E. What's D? Huh? Oh, the variance. Okay, that's, so this is D? Oh, this is C? This is D? Oh, they split up into two. Okay. And now E is find an estimator for, so this says capital R is a non-biased estimator for little r, and it has a nice variance. Gets small when you interview a lot of people, right? That means there's not much variability. It means the estimate has some accuracy. How would we estimate this? Q. That's the thing we want to know, little q, proportion of population that actually have the property in question. Well, if we look there, we see how little q is related to the real value, little r. How can we estimate little q? Well, we can estimate little r by what random variable? Capital R. So if we define capital Q, to be capital R plus P minus 1 over 2P minus 1. This should be an estimator of little q, because this is an estimator of little r, and when you have little r in here, you get little q there. And this is a pretty reasonable function of this variable, right? It's just you add something and divide by something. That's continuous. It's a linear function, in fact, of the variable little r. What about the expected value of q? Is this a non-biased estimator of little q?
Yes.
Well, do you agree with that? Okay. And what's the expected value of capital R? Little r. So I put little r here, and then I rewrite it the way I had it before. It becomes little r plus p minus 1 over 2p minus 1. And what's that? That's little q. So it's an unbiased estimator of little q. And what's the variance of capital Q? Let me ask a question. If C is a constant, what's the variance of x plus C? Variance of x. Why is that?
This is just going to shift everything, so it doesn't change the value.
Exactly. It just shifts things. It doesn't change how it's spread out. Okay. So here we have something like that, right? We have the variance of r over 2p minus 1 plus p minus 1 over 2p minus 1. So here we have a random variable plus a constant. The addition of the constant doesn't change the variance, so we just drop it. And then when we're multiplying a random variable by a constant and take the variance, you pull the constant out, but when it comes out, it becomes squared. And we computed the variance of r over there, and we got little r, 1 minus r over n. Like that. So how would you pick p? Would you toss a coin if you're doing this experiment? If you're doing these interviews? Would you take a coin toss to decide whether the interviewee is going to answer question 1 or question 2? Why not?
You'd want it to be bigger so that the variance is smaller.
Yeah, what would the variance be if p is half? Doesn't look very good, does it? So you shouldn't take a coin toss here. Maybe roll a die. If it comes up 1, question 1. If it comes up the other one's question 2. All right, now 29 was similar. The only difference was in here. Question 2 wasn't, is it true you did not do A? It's more like, do you have blue eyes? Something like that. Or were you born in June is what they use. So it's some other question which the interviewer knows the answer to. Maybe they fill out a form telling what month they're born in. There's probably no reason to lie about that. So maybe were you born in June? So the probability of a yes given question 2 is not going to be 1 minus q anymore. It'll be some other number that's known, alpha. So for example, if the question was, were you born in June? Alpha should be maybe 1/12. Okay? And now you go through all of this where you replace 1 minus q by alpha and follow all the steps that we just did. Okay? So alpha goes here. That changes this a little bit. So maybe we'll so this would be our value r. And then we want to solve this for, does everybody agree with that? This gets replaced by alpha. This is probably yes if question 2 is asked. Solving for q. You get this. Capital R is still going to have these two things true, where R is probably the yes response. So you approximate little r by capital R, which comes from the data. That's this thing. And then capital Q would be capital R minus this over this. Okay. And similar thing over there then. So it'd be on unbiased estimator again. Okay, so any questions on 28 and 29? Okay, good. All right, so let's return to and finish stratified sampling. Total population is the sum of the numbers in the various strata, and the weight of the nth strata it's just the proportion of the population that's in the nth strata. As before, the population mean is this. But if we think about this sum for a moment, how could we do this sum? This is the population total, right? We could take the total in strata 1, and the total in strata 2, and the total in strata L, etc. Like that. And I would probably call the mean in strata L this thing. Right? That would be the population mean in strata L. How do you get the mean from the total? You divide by the total, by the number of members. Since TL is NL mu L, I could replace TL by that. Now I can move the 1 over n inside. And in terms of the weights, we could write it that way. And this is, we did this last time already. So the population mean is the weighted average of the strata means. And the weight is just a proportion of members of that strata in the whole population. Okay? Any question about any step here? So the object is to approximate mu. And let me insert in here by simple random sampling. Okay, so in each strata, we perform simple random sampling. We take little n sub L individuals from the Lth strata. The random variables for the Lth strata are denoted x1 L, x2 L, x n sub L, L. The second one indicates what strata they're from. First one indicates which different individual in that strata. So there are n sub L of these. They're not independent. Why not? Why are these not independent? It's from simple random sampling, right? There's a slight dependence. So we know, for example, that the covariance of xil and xjl would be minus sigma squared over little n sub L. Was it minus 1 here?
It's capital N sub L.
Well, oh yeah, capital N sub L, yeah. Thanks. If I is different from j. Okay, so these are not independent. They still have this. This is simple random sampling, but on a subclass of the whole sample. But if I compare for different L's, they will be independent. They're independent for L different from K, right? This is useful because then the estimator for mu would be xs bar, which would just be the let's look at this equation. Mu equals some L equal 1 to, oh no, I did it again. I switched from capital L to capital N. This is capital L here, sorry. Okay, so let's look at this. Mu is this. Okay. So we want to estimate mu. How do you estimate the mu? You take the sample average. Okay. How are we going to do this with strata? How do we estimate mu L? We take the sample average of the Lth strata, then we multiply by the weight, then we add up over the different strata, and that'll give us an estimator for mu. So this will be WL x bar L, I'll call it. Where x bar L, I think that's the notation from the book. Yes, it is. We add up all the samples from the Lth strata, divide by the number of samples in the Lth strata. That's an estimator for mu L. We insert it in here. That'll give us an estimator for mu. And in fact, when I take expected value of xs bar, what do I get? What's the expected value of xl bar then? It's mu sub L. So when I take the expected value of this, what happens? Well, I take the expected value over here. And this is a constant. So you get the expected value of this. This is mu L. So I get mu is the expected value of xs bar. So xs bar still gives us an unbiased estimator of mu. And using the independence of different strata, we can easily compute the variance of xs bar. First of all, what's the variance of xl bar? Well, this is just a simple case of simple random sampling of a population of size capital NL, sampling little n sub L individuals. And do you remember what that was? It was sigma squared over n, sigma L squared over n sub L. Well, all these random variables have the same sigma, so I won't do it. Sigma squared over n sub L times a population correction. Oh, was it? This is right, yeah. Right? Okay, that's from just plain old vanilla simple random sampling, not stratified in any way. Okay? Now let's compute the variance of x bar s. S for stratified. Well, what about the XL bar random variables? Those are random variables, right? There's means from the different strata. The random variables in the different strata are independent, so the sample means from the different strata will be independent random variables. So here we have XS bar is a sum of independent random variables. And when you take the variance of a sum of independent random variables, what do you get? You get the sum of the variances. And when I take a constant times a random variable, take the variance, I can pull the constant out and square it. Okay, so here I use independence of the different random variables, random samples from different strata. This is different from their independence within the strata. They're not independent within the strata, but we're not using that. We're using independence of different strata. Okay, and what's this? Well, I just substitute that in. And I get that. Yeah.
Is there a reason that the sigma squared for the variance of the x bar
Oh.
doesn't include?
No sigmas. Okay, did I answer your question? Okay, was that what it was? I shouldn't have put the L there. Yeah, question here.
So does that mean each strata has the same variance?
So the sigma squared is the variance of any individual random variable in here. Okay. So do you remember the variance of xi was sigma squared in simple random sampling, and that's the sigma squared here. Okay. And the variance, so the variance will be the same of the random variables from the individual random variables from different strata will still be the same. Okay. And if you ignore the population correction term, it has a very simple look. It looks just like this. Okay, so we did all this last time. There are simple corrections for totals that I'll let you look up in the book. Okay, now, so there's our variance. Let's say we ignore the variance of our estimator is approximately this, sigma squared okay, so let's revisit the variance business. Okay, so this is all true if the variance is the same. Then everything I said is true here. In fact, the only place that the variance comes in is at the very end when we're computing the variance of the estimator, or here, for example, computing the variance of the estimator in the nth strata. But now, it's not always the case in applications that the variance would be the same in different strata. So what would some examples be? In the hospital example, if you had a hospital with not very many beds, and you compared the discharges in a month for hospitals with a small number of beds with the discharges in a month for hospitals with a huge number of beds, which one do you think would have a larger variance or more variability? Or do you think it would be about the same? That a hospital with maybe 100 beds would be discharging, the variability in how many patients would discharge per month would be about the same as for a hospital with 1,000 beds, or would it be different? The one with more beds should have a larger variance. Or if you're asking, say, in a population, how many languages do you speak fluently? And you ask this question in North Dakota. What do you think the variability would be there? You may not have been to North Dakota, but you might have some image in your mind of what it's like in North Dakota. Do you think people there would be fluent in a lot of different languages, like individual? Probably not. Okay, probably should be one. Most people would say one. Now come to California, and you ask people how many languages are you fluent in? Would there be more variability there?
Yeah.
Yes. Okay. All right. So I think you could think of other examples where you might split a population into different groups, and in these different groups there'd be different variances for the measurement you're making. And the variances are different in different strata. Okay. Another question might be household income. Suppose you look at household incomes in North Dakota and household incomes in Southern California. In North Dakota, there wouldn't be a lot of people at the very high end, I don't think. Most people would be middle class, working class, so the incomes wouldn't fluctuate very much. But in Southern California, do you think there's much fluctuation in incomes? Have you seen Rolls Royces and Lamborghinis here? Maybe you've seen cars that look like they could barely move. So that's another example where the variance might be different in different strata. So if we come back here, that would mean that here we would put an L for the variance for the Lth strata. And here we'd put a little L. And here we wouldn't factor this out now. Okay? Okay, so that's what it would look like if you have different strata. And that's more typical. So, given these variances, okay, so let's suppose for a moment that we know the variance is sigma 1 squared through sigma L squared. And you can take a sample of this size. You don't have unlimited resources, so you take some smaller sample. How should you choose N1 through NL? Well, let's see what effect the choices have. Does the choice of N1 through NL affect whether the estimate X bar S is unbiased or not? Does it affect whether it's unbiased? No, expected value X bar S is mu. It doesn't depend on the choice of the n, little n's. Okay, so that we don't have to worry about making the estimator X bar S unbiased by a peculiar choice of N1 through NL. Does it affect the variance? Yes, it does. Doesn't affect this, it doesn't affect that, but it does affect this. And what would you like the variance to do? Would you like it to be big or small when you're making estimates? Small. So we want to take the variance to be n sub L's so that the variance is as small as possible. So that the variance of X bar S is minimized. Okay, so how do we do that? Well, here's a function of capital L variables, and we want to find its minimum, but it's subject to a constraint. The constraint is we're taking a sample of this size, so we want to minimize f of n1, n2 through n sub capital L equal sum little l equal 1 to capital L sigma little l squared w little l over n sub L subject to Okay, so this is a minimization problem. You've probably seen this kind of thing before. And we'll do it after the break. Okay, let's do this minimization. You may recall the extrema occur where the gradients are pointing in the same direction. So we just have to compute the gradients of these two functions, f and g. Gradient of f is this. Oh, no squares on the W, sorry. Oh, yeah, there is squares. There should be there. Right. The square is missing here. Okay, so I'm going to minimize this estimate that you get from ignoring the population correction. Here is a W squared term. And what was F? It was the dependence on the n sub L was 1 over NL. And what's the derivative of 1 over NL with respect to NL? It's minus 1 over NL squared. Okay, so I think that's... Grad G is this. component will be the derivative of g with respect to n sub l. Derivative of g with respect to n sub l is 1. And when are these lined up? You have to have this equation Why is that? What does this equation say? It says that the components here must be equal to lambda times the components here. What are the components here? They're all lambdas. So all these all have to have the same value. In other words, they don't depend on L. Or if I flip it, and take square roots, okay. Well, what does that say? We have this piece of information, and maybe I'll call this lambda. Can we tell what if we solve for C, if we can find CL, then we know what the N sub L should be. Okay, well, let's multiply. So we know that there's some number lambda so that we want this to be true at the minimizer. At the minimizer, this is equal to some number lambda for all L. So that means that NL is lambda times sigma L WL for all L. And if we sum them up then, this is little n, and this would be lambda times the sum, L equal 1 to capital L, sigma L, WL. So lambda is n over sum over L equal 1 to capital L. Maybe I'll write it as k equal 1 to capital L sigma k WK. All right, so let's repeat this. We know that at the minimizer, the number NL over sigma L WL doesn't depend on L. So that means it must be equal to some fixed number lambda. Okay? I just solved that for n sub L and use the fact that the sum of the NLs must be n. Okay, but I use the fact that this number is lambda times that number to express n as this sum. Okay? I change the index when I go from here to here because I'm going to use a different index in a minute. I didn't want it to be confusing. So that's lambda. So what's n sub L? It's lambda times this. So I multiply this by sigma L WL. Okay, so that's the number C sub L. So that's a proportion of the sample that should be taken from, this is the proportion of the sample that should be taken from the Lth strata. So how many do we take from the strata L? This proportion times the total sample. So would all strata have the same sampling size to get an optimal variance? In other words, a small variance? No. If the variance is big and the population size or the population size is big in such a way that this is a big number compared to that, then this would be big, right? If the variance in a strata were small and the population wasn't too big, then you wouldn't sample many from that. But if the population is reasonable size and the variance is very big, then that strata would get more, you'd want to sample more from there. And if you do the sampling in such a way that you pick this many from the Lth strata, that'll minimize the variance, so you get a better estimator. So there's a little table in the book. It's example A from section 752, where it's the hospital example again. Hospitals are split into 4 nearly equally sized strata. From smallest to largest in terms of number of beds. The number of hospitals in each strata is about the same. Because the number of hospitals wasn't divisible by 4, one extra had to go in here. So in strata A, you have 98 hospitals that have the fewest number of beds. Then the next strata would be composed of the next 98 hospitals in terms of number of bed sizes. So every hospital in this strata has more beds than every hospital in this strata. And then this would be the next 98 biggest one. So every hospital here has more beds than any hospital there or there. And these are the biggest 99 hospitals in terms of number of beds. Okay? And 98 is a number in strata 1. 98 is a number in strata 2. 98 is a number in strata 3. 98 is a number in strata 4. Relative weights are almost a fourth. The total number was 393. So this is 0.249. What is this? This is n sub L over capital N. So this would be 98. This is 98 over 393. This would be 98 over 393. The mean in each one is 182.9, 526.9, 956.3, and 1591.2. And sigma L, and each one is 103.4, 204.8, 243.5, 419.2. And this column bears out the need for considering different variances in different strata. And this is what we mentioned before. This is what we expected. If a hospital has more beds, you can see the average number of beds in the hospital here is 1,591. Then there'd be more variance. Oh, I'm sorry, this is the number of discharges. Here we don't know the number of beds actually. This is the number of discharges in a month. So the number of beds must be big. And in fact, this was the strata with the largest number of beds, and the variance there was largest. And so we would use this number and this number to come up with the optimal sampling numbers for the various strata. Okay, so by squaring these numbers, multiplying the corresponding ones to did I get this? Let me just check. Yeah, okay. You don't square them, I'm sorry. You multiply this times this, add them up, multiply that times that, take this ratio, and here's what you get. Okay, so once you've decided what the sample size should be, the total sample size, the number you should take from strata 1 should be approximately 0.106 times that. Now this may not be an integer, but maybe you take the closest integer to that. This number taken from strata 2 should be 0.210 times the total number, etc. And this will minimize the variance. So you can make the variance small by suitably adjusting the sample sizes from the various strata. So that's why you would do stratified sampling. It can give you better estimates. Yeah.
I just have one question on this.
Yeah.
Why would we really care about what we just came up with if we already knew everything about the strata that we wanted?
Okay, well, let's suppose you didn't know this. Oh,
Oh, okay, so if you want to build it for that.
yeah. Suppose you did know this. Okay, yeah. Okay, so these are the true things, but yeah, suppose you didn't know that. You wouldn't want to, right? Everything's known, then you don't have to sample, right? But if you didn't know this column, but somehow you knew this one, okay. But now that's a big if. We don't always know these things. Of course, you could get estimates for these using samples, but then that means you've already sampled. And now how do you pick these? So what do people do in the lack of knowledge of the sigmas? They do what they call proportional sampling. They just use if you don't know the variances in the strata, I believe it would come out to be this. Right, you just sample from the Lth strata the proportion of individuals in the Lth strata compared to the whole population. If you add these up, what do you get? Well, when you add these numbers up, you just add up these numbers. What's the sum of the n's, capital N's of L? It's capital N. The sum of these becomes 1. So the sum of this would become little n. Okay, so if you don't know sigma squared, you could use this. You give up optimality, but what else can you do? Okay, it's a reasonable approach. Okay, so let's leave that behind and start chapter 8. Okay, so in this chapter, we consider problems like this. This is a very important problem, I'm sure. So why would this be a Poisson random variable?
Wait times.
Kind of. What about individual leaves? If one leaf is about to fall from one branch, does it affect?
No.
No. So we have a whole bunch of independent random variables. That is, what are the independent random variables? Well, there are a lot of leaves. So there's one random variable for each leaf. The random variable 1, if the leaf falls, and 0 in the next hour, 0 if it doesn't. So the number of leaves falling would be the sum of all these random variables. The probability the leaf falls is small, so number of leaves times the probability of falling would be some reasonable size number. So we use the Poisson approximation to Bernoulli and decide that this should be Poisson random variables. So there's some mathematical or scientific argument that this distribution should be Poisson. Now I can replace leaves falling from a tree by alpha particles emitted by, in the book they use the substance americium, I think, or chinium. I don't know how to pronounce it. americium emits alpha particles. Number of alpha particles emitted in an hour would be a Poisson random variable. This is based on mathematical reasoning. But now, once we've decided that, we want to estimate the parameter in the Poisson random variable. Okay. There's another example in the book. Where they talk about the current across a cell wall. Current is determined by opening and closing a lot of little channels in the cell wall, and things pass through. The channels are open with some probability, closed with some other probability. There are many, many of them. So the net current would be decided by how many of these channels are open. And so we're adding up a bunch of Bernoulli random variables. And so we'd want to use a normal approximation. So the net current across the cell wall would be modeled by a normal random variable. But you want to decide what mu and sigma squared are. And then you might, in fact, make some deduction about the properties of these channels that are opening and closing. How many of them there are, for example. How much can pass through an individual one. Or does this happen to you? Your 7th car in line. The light turns green. You want to go right away, but alas, after some interval, the first car moves. After some interval of time later, there goes the second car. Finally, the third car, you're starting to wonder whether you'll get through because the light might turn red. Maybe even are tempted to honk. You might say something. Anyway, so there's some random amount of time you have to wait. And this is a gamma random variable. That's one reason to, there are reasons to model this as a gamma random variable. How do gamma random variables arise? One way is as a sum of independent exponential random variables. And if you think of the time from the movement of the turning of the light green to the movement of the first car as being an exponential random variable, and then from the movement of the first car till the second car moves as being another exponential random variable, etc. Then and your order in line would be some random variable too, like you might be 7th, you might be 8th, you might be 2nd, you might be 1st, you might be the guilty party who waits forever. So typically, and what's the sum of independent exponential random variables is gamma. So this might be modeled by a gamma. But then the question is, what are alpha and lambda? Okay, so how could we estimate these things? We take samples. And in this chapter, we'll take independent samples of the phenomenon involved. And we'll estimate the parameters of the underlying distribution. So a lot of times there will be arguments that tell you what shape or type of underlying distribution you have, and then you have to try to find the parameters for that type of distribution. So for here, it's Poisson, there, normal, there. There's another argument for gamma. Okay, so here, maybe you would watch one oak tree for a while, maybe an hour, maybe two. Then you go watch a different oak tree for an hour, and then go watch a different oak tree, maybe try to pick them all about the same size. And this is the number of leaves falling from oak tree 1 in an hour, from oak tree 2 in an hour, oak tree n in an hour. Or you might observe n different cells and measure the current. X1 would be the current across the cell wall in cell 1, X2 in cell 2, etc. And here you might observe n different drivers and see how long they have to wait at a traffic light. Okay. All right, so the problem of estimating parameters can sometimes be done by expressing the parameters as functions of the moments. if x is Poisson with parameter lambda, the first moment of x is lambda. So I call that mu. Mu, the first moment. Maybe we use mu with a subscript? Or do we use mu with a superscript? Mu2, I guess we could decide. Okay, so the first moment of x is mu sub 1. It's equal to lambda. So in this case, we want to express the parameter as a function of the first moment. And what is it? What is that function? F of mu1, f of x is x. Okay. Let's suppose x is normal with mean mu and variance sigma squared. And mu1 is the expected value of x, and mu2 is the expected value of x squared. How can we express mu and sigma squared in terms of these moments? Well, mu is mu1, right? So in this case, f of mu1 is mu1. f1, I'll call it. We need two functions this time. Sigma squared, I want to express that as a function of mu1 and mu2. Well, sigma squared is mu2 minus mu1 squared, right? It's the second moment minus the first moment squared. So here we've expressed the parameter mu in terms of turns out just the first moment is needed here. And we express the second parameter, sigma squared, in terms of the second moment and the first moment. Final example, let's do the gamma. The expected value of x is good memory, because that was question 1 on the final exam, right? And what's the expected value of x squared? So this is mu1. And mu2. Remember how I do that? What's the density? To get the expected value of x squared, I multiply by the density by x squared. So this is lambda to the alpha over gamma of alpha. And what's this integral? It's gamma of alpha plus 2 over lambda to the alpha plus 2, right? Which would be gamma of alpha plus 2 is alpha plus 1 times alpha times gamma of alpha. So gamma of alpha plus 2 over gamma of alpha would be alpha plus 1 times alpha. Here we have lambda to the alpha, there's lambda to the alpha plus 2, so it's lambda squared down here. Okay, and so how can we express, we want to express alpha as a function f1 of mu1 and mu2. And we want to express lambda as a different function of mu1 and mu2. Yeah. But we have to express lambda now as a function of mu1 and mu2. Can we do that? you can, of course. There are two equations and two unknowns. Let me write down what the answer is. So if I take mu1, divide by this minus that squared, I'll get lambda. I'll let you check that. Now up here it says alpha is lambda times mu1. And here I have an expression for lambda in terms of mu1 and mu2. So I just multiply this times that. And that's f1 of mu1 to mu2. So in each of these cases, you can express in a fairly straightforward way the parameters in terms of the moments. Okay. Now, when you take samples, you can estimate the moments. And if we plug those estimates into these functions, then we'll get estimates for the parameters. This is called the method of moments. Okay? In the sense that this is the law of large numbers. Assuming it applies. Mu1 is an average of these random variables. If they have a finite expectation, that average would converge to the expectation. That's this thing. Mu2 is an average of independent random variables. If they have an expectation, it would be mu2. And the law of large numbers says mu2 hat, which depends on n, would go to mu2 in this sense as n goes to infinity. So mu1 hat and mu2 hat can be used to estimate mu1 and mu2. And then if we know how to express the parameters as functions of the moments, we can plug in the estimates for the moments, and we get estimates for the parameters. So for example, let's look at Poisson. The first moment is the parameter. So how do we express the parameter in terms of the first moment? It's just the first moment. So what would our estimator be for lambda? Lambda hat equal mu1 hat is the estimator for lambda. in the case of Poisson. In the normal case, how would we estimate mu? Well, it's a function of mu1 alone. In fact, it's mu1 hat. And how do we estimate sigma? We plug in mu1 hat here, mu2 hat here. That gives mu2 hat minus mu1 hat squared. And this is for normal. And finally, for gamma, how do we estimate alpha? Well, alpha would be mu1 hat squared over mu2 hat minus mu1 hat squared. And for lambda, we put in mu1 hat, mu2 hat here. So it gives mu1 hat over mu2 hat minus mu1 hat squared. Okay. And next time we'll talk about the statistical properties of these estimators using, say, law of large numbers, central limit theorem, or law of rare events, things like that. So we treat these we look at the distribution of these estimators. Okay, but this is the method of moments.